Okay, so this is about the screw, and of course a car jack is using a screw. And so here we have the simple machine. In fact, I already lifted up. I think you can see that right here. And I notice it takes quite a bit less force. Okay, I'm going to mention a few numbers, but don't write them down at that point. In fact, I will explain in a moment here why not. Okay. I take this car regularly to the dump to get rid of the garbage, and they have an electronic scale there, and it always comes in at like 4,000 some pounds, and when it's empty without the garbage, pretty much exactly 4,000 pounds. Well, I have a couple of kayaks on top of the car now, and then I have some stuff inside, so let's assume that the total mass of the car right now is 4,200 pound mass. And again, don't write that down at this point. Okay, with the car jack, I'm lifting only a quarter of the entire car, so approximately 1,050 pounds, which we calculated would be 480 kilograms. However, I'm actually not lifting the tire or any of the suspension here of the axle, so it should be actually appreciably less than those 480 kilograms, and of course the engine block is in the front. And so at this point here, as we're filming, I really don't know how much it is, and I hope that I get a better estimate later on and put it as a caption into the video. Anyway, we lifted it up. As we lifted up those 480 kilograms, which is really not the mass of what I'm actually lifting, it's appreciably less, but that would be in the neighborhood of 4,700 newtons. And when I applied the force here, I came up with I'm only measured 50 newtons. It was actually relatively easy to do, and it's hard for me to do that here by myself as Jerry is filming here. Yeah, I think you can almost see it actually here. Yeah, in fact, I can hold it and you can see it. It's about 40 newtons what it measures here. But of course it's a little bit dangerous here, so I don't want to do this whole thing over again. So I measure about 40 newtons, which means I have like an actual mechanical advantage of approximately 100. 4,700 divided by 40, or over 100, so it's like extreme mechanical advantage. I doubt that. I think what I'm really lifting is much less than 4,700 newtons, or 1,050 pounds, or 480 kilograms. Much less than that. Okay, anyway, I lifted it up to a certain height. We measured that. Again, I'm also not going to mention that, but now I'm going to let it down, and the only thing that I do during the video here is I count the rotations that I let it down, and that of course would be also the rotations that I put in. So it's the number of rotations times 2 pi times the radius. We measured this one here to 22 centimeters. That would be the amount of distance that I have to apply that 40 newtons of force through. And that one is actually a real measurement. In fact, I didn't use these ones here because the force was actually small enough that it hardly registered on this one here. So that's why I'm using this one here straight from a physics lab, which is actually pretty strong, and I measured 40 newtons, which is roughly 10 pounds. So I guess maybe this could have measured. Oh well. Okay, so I'm going to let it down, and I'm going to count the rotations. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I'm going to count a little more, but you notice I probably lost count a little bit by 1 or 2. Oh well. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, that's at this point I'm actually done, and I noticed that in between 10 and 20 it actually got a whole lot easier, which means I'm really not lifting that mass that I estimated earlier. In fact, I'm going to leave it. Yeah, so I have about 20 here. I'm just going to measure the height here, and it's 73, and earlier I measured 82, so I lifted it by about 9 centimeters, which is 3.5 inches. But of course I had to do 20 rotations times the radius times 2 pi, and that would give me the whole distance compared to just lifting it.
This is the analysis for the example data for the screw, which was a car jack that I used to jack up my car. And here is a narrative that I'm just going to read. The scale of the Central Kenai landfill shows usually quite exactly 4,000 pounds for the weight of my empty Dodge Caravan. That includes actually me, and they have an accuracy of plus minus 20 pounds. And then once I measured it, that of those 4,000 pounds, 2,300 are in the front and 1,700 are in the back. So I just put the 2 front tires on the scale and the 2 rear tires on the scale. On the day I measured it, I had kayaks on top and some totes inside, which I estimate that's an extra 200 pounds, but I wasn't inside. So minus 200 pounds, which means it's still those 4,000 pounds. Now we jacked up the rear ride, which should be a half of the weight of the rear, thus 850 pounds. However, the tire axle and suspension were still on the ground, and here this is a really gross estimate that is some fraction of that 850 pounds. So I surveyed a few people that gave me their opinion, including a few students, and I came on to a consensus of that. Well, it may be around 600 pounds without the tire axle and suspension that I'm actually lifting, and that's what my data are about. And then, oh, I didn't mean to get this one here. Okay, and here's the okay, and here is the analysis of those data. So I'm going to put in here that these I estimate to be 600 pounds, pound mass that is. Correct American unit would be slugs for the mass, but I'm just going to use the pound mass, and I convert that to kilograms, and so that's 600 divide by 2.2, and that gives me the 272 kilograms, or around 270 kilograms. After all, this is a very gross estimate here, 600 pounds. I should really just use one significant figure, which I think I'll do at the very end. Okay, weight of the load. Well, that's simply multiplied by 9.8 or around 10, so 2,700 newtons. The height, well, that's the height that I jacked up the car, and I measured 0.09 meters. And the work that I would have to do without actually using a car jack, so that would be then 2,700 times 0.09 meters. 0.09 meters is 9 centimeters or 3.5 inches. There you go. 243 joules, or simply 240 joules. The lead of the screw is this one here. It's the distance between adjacent spiral, and this one here on this car jack here doesn't look like a spiral, but you can imagine that it should be. In order to move through here, it needs to be spiral. So the distance between the the distance between two consecutive spirals is 0.5 centimeters or 0.005 meters. Incidentally, that's also the radius of the shaft, so 0.005 meters. The radius of the handle itself, and that would be, oh, they don't show the handle here, so that's the one that I would have to attach right here. So I have a lever arm here, and that's 22 centimeters, roughly 8 inches. So 0.22 meters. Then the mechanical advantage is 2 pi times the radius of the handle divided by the distance, the lead of the screw. So that comes out to 2 pi times 0.22 divided by 0.005, and that's a whopping 280 times rounded mechanical advantage, which is certainly something I want, because I cannot lift 2,700 newtons or 600 pounds by myself, and it should be relatively easy to do with the car jack. So here's my mechanical advantage, 280. When I calculate therefore the expected effort force, I come up with, divide the load 2,700 newtons by the ideal mechanical advantage of 280. So divided by 280 comes out to around at 10 newtons. By the way, the ideal mechanical advantage doesn't have any units because it's the ratio of the same unit measurements. So here, that's only 10 newtons. That's only about 2 pounds. It's kind of what I expect when I turn a handle, that I only exert 2 pounds. And when you jack up a car, you notice that it's actually relatively easy to do that with a jack. So huge mechanical advantage. That's expected, at least. That's the ideal one. The actual one could be quite a bit smaller still. Okay, number of rotations. I measured that in order to jack it up. That was 3.5 inches, 9 centimeters, 0.09 meters. I had to rotate the handle 20 times. And then the distance that I rotated, that's actually quite a bit. So that's 20 rotations times 2 times pi times the lever arm of 0.22 meters. And that comes actually out to 28 meters, which means I had to rotate the handle approximately 80 feet, which is quite a bit, but of course I expect that too, because I am not going to have a free lunch here. That ideal advantage over here is going to kick down my force appreciably to the 10 newtons here from original 2,700 newtons, but when I jack it up 0.09 meters, well, I have to rotate that handle quite a bit, those 28 meters. So that's where, again, the mechanical advantage goes in and tells me that, hey, but you have to rotate a whole lot more than you actually lift it. Okay, the actual measured force was 40 newtons, which is actually 4 times as high as what the expected effort force should be. Ideal or expected effort force versus actual measured force, of course, that one here does not take into account the friction that's involved when I turn. It's between the handle and the perhaps little eye that you saw here. Sorry that I don't have a handle on here. And then of course the friction in here, the friction in there. So that all plays in. Alright, then the work with the lever, with the screw or lever, that would be then 40 newtons times 28 meters. And that comes out to around at 1,100 joules, which is quite a bit more than doing it without using the car jack. But then again, I need the car jack because otherwise I can't lift it by myself. So I take that into account. Of course, this one here is all the energy that got lost due to friction. Okay, the actual mechanical advantage comes out to dividing the force of the load, which is the weight, 2,700 newtons, by the force that I actually measured, so 40 newtons, so 2,700 divided by 40. So that's around at 68. And then finally the efficiency, which is divide the 240 joules just lifting the car with bare hands by the 1,100 joules lifting the car actually with the car jack. So kilojoules divided by 1,100, and that comes out to 22%. And earlier I said something about my estimate here. 600 pounds is really one significant figure, so my end result I should just put into one significant figure, about 20%. And those are the example data for using a car jack.
Go. Okay, so this is about the inclined plane. In this case it's a ramp, and I think I have to speak up because there are cars here and we're outside. Okay, so I'm going to pull it all the way up the ramp we measured earlier. That's 24 meters. I put all this weight in here, which is pretty much a couple of buckets full of water. If you want, come over here and just show that there's a lot of water in here. And this one is full of water to put enough weight in there. We weighed everything earlier and we came up with 64 kilograms for the entire thing. And if I try to lift that, I am not very successful. So rather than lifting it up the stairs, I'm going to use this ramp here, which should be relatively easy. And of course you can see that I can pull this easily. So I'm going to attach the scale here. Again, this is measuring in pounds. I have to see that what it's doing in the horizontal. In the horizontal it's actually almost zeroed, so that's pretty good. I don't have to add or subtract anything. Okay, and then I'm going to pull here, and I'm measuring about, actually this time around, let's see, I'm measuring only 12 pounds. Earlier we measured a little bit more, but let's go with the 12 pounds that I just measured. Okay, so here we go, and then I just pull it all the way up. And this is pretty easy. Of course, I'm not going to get a free lunch. I have to apply my effort for a much longer distance for these 24 meters here, which is about 70 feet. While over there, if I lifted it up the stairs, I had to exert a huge amount of force, kind of like 600 some newtons, or about 140 pounds to lift, but I only would have to lift it 0.87 meters up the stairs. Again, I'm not going to get a free lunch here, but that would be a whole lot harder, which of course is the idea behind a simple machine such as the ramp, to reduce the amount of force with which I pulled versus lifting it. But again, I have to apply that over a much longer distance. Okay, so again, yeah, I measured 12 pounds. The mass of the entire assembly here is 64 kilograms, and again, unfortunately, this is measuring in pounds. Oh well. And then the entire length of the ramp is 24 meters, and if I lifted it up the stairs here, we measured that as well. It was 87 centimeters, roughly 3 feet. All right, good. Thank you. Okay, so this is the block and tackle that we have set up here. It's a bigger, more industrial version, and I'm trying to talk as loud as I can because there's a lot of noise coming here from the refrigerators in the cafe over here where we have set it up across from that. So anyway, we have the block and tackle here, a couple of pulley systems here, and so these I got these at a hardware store, and then somebody welded this one onto me because it's missing the eyes over here, so I needed to attach it, of course, here. And then also this one doesn't have an eye here, so we had to tie it from the top here, which means that we actually have 4 segment lines running down, so an even number. When you tie it to the top here, you have an even number. Anyway, so we're gonna we put a load on here, that bucket here, and I had measured it. We had put half full with half amount of water. And this one here is also half water, and I believe we measured 25 pound mass for the mass on this one here. Okay, so which means that this one is also 25 pounds in here, and you just saw a moment ago that I had to lift quite a bit here. Well, over here I have the hauling line, and I attached the spring scale to that, so I'm going to measure that in a moment, and you will see it's going to be relatively easy for me to do. Still have to put quite a bit of work and force into it. Overall, I should have an ideal mechanical advantage of 4 because I have 4 segment lines running down. Of course, I'm not going to get a free lunch because I expect that I have to pull this 4 times as much on this side on the hauling line in order to lift the bucket up all the way here, which I had measured to 70 centimeters or 0.7 meters. Okay, so now I'm going to take the measurement here. And if you could come over here, and I'm going to pull on this one here, and it measures, oh, I turn it around, I want to measure newtons. I measure, I want to say 40 newtons, 41 newtons, there we go. So 41 newtons is how much I measure. 41 newtons is about 10 pounds, a little bit less, and I think you can see that this is a whole lot easier than trying to lift the bucket. But still I have to put quite a bit of work in, and you see that I have to really pull a lot of hauling line in order to get at those 0.7 meters or 2.5 feet up. And then I better release it slowly. And that's my measurements for a more or less industrial pulley system block and tackle. Okay. Okay, so this is about the lever, and more or less an industrial lever, which is the shovel here with which I'm gonna lift the armchair. And I have to say it already that this is a whole lot easier to lift at least half the armchair with the shovel than compared to with me lifting it by hand. Okay, we took a few measurements ahead of time. We have a couple of scales here, if you could come over here, and Jerry's the one filming, and he helped me with this experiment. And he stood on one scale, I stood on the other one. We measured our mass, then we both carried the armchair on it and measured the mass of the armchair, which came out to 33 kilograms. However, what I have to remember is because with this lever I'm only gonna lift half the armchair, I wrote down 16.5 kilograms as the mass of half the armchair. Okay, then, and that pretty much was the only thing we did ahead of time. Well, that's not true. I'll show you in a moment. But what I'm going to do here now is I'm going to attach this scale here, the spring scale, which unfortunately only measures in pounds. And if you can see that, if I hold it right side up, it's already a little bit off. But it so turns out that in order to hook it into the lever here, I have to hold it upside down. And here it's actually quite a bit off, and we figured it's about 2 pounds off. And this may not show, so I'm just going to say that actually I have to add about 2 pounds once I have measured. Okay, so now here, pull on here, and there we go. And then I'm measuring about 10 pounds plus the other 2 that I had. So 12 pounds is what I measure in lifting this armchair. And then the height, we measured that earlier, that I'm lifting it off the armchair to a height of 16 centimeters, and I pull the lever down to by 57 centimeters we came up. So lift here 16 centimeters and then pull this one down by 57 centimeters, and all the rest here can be calculated with the data that I just gave. Okay, thank you.